Okay, well, let's get started. Welcome to the Bay Area Ray Community Meetup Talks, the first meetup of the new year. My name is Jules Damji. I'm part of the Ray advocacy team over here. I'm delighted to see you. So many have actually joined us from different time zones. Always happy to have all these people who actually take time to join us. Dimitri, welcome. Thanks a lot for joining us. A couple of logistics I would just want to make it sort out so that we actually can run this thing tonight smoothly. All your mics are unfortunately muted, so we can't hear you, nor can we actually see you. If you have any problems regarding the slideshow or regarding the notebook that you can't really see the font, do please put it on the chat and we'll try to sort it out. I do have, I have to change settings to. Yeah, it is actually enabled to everyone, so everyone should be able to actually put things on the chat. If you have any questions for the Q&A for the speaker, please put it in the Q&A section because it's easier for me to manage and run it rather than scrolling up and down the chat window because I can actually lose that quite easily. So put all your questions for the speakers in the Q&A sections, and towards the end of the talk, I'll try to moderate and then put those questions to the speaker who can answer it. So much for the logistics. Let's get really started with the session today. Here's the agenda. Normally, for the first few minutes, I'll give an announcement or some of the upcoming events which are coming up. And I think it's nice to actually reflect back on how the Ray community and Ray did in 2022. So I'm going to briefly, for about 10 minutes, give a high-level view of some of the accomplishments that the Ray team and the community together have achieved in 2022. And then we have two good talks, how to actually prevent your pernicious error, error using the Ray monitor by Clarence. He's part of the Ray team focusing on Ray stability and observability. So he's going to share that with us. And then we have a Ray community user from Shopify, Kshetrajna Raghavan, who's going to tell us how they actually use TensorFlow and Ray building hierarchical models with billions of products. So I think that's going to be a good evening of Ray illumination, pun intended over here. And so a couple of announcements. As you know, we actually had a very successful Ray Summit last year, and the CFPs are open for Ray Summit again. We started about a month ago, and so they open till the February the 17th, I think about 3 weeks from today. The conference is going to be held in person, so if you decide to submit the CFP and if it gets accepted, do make sure that you can actually travel wherever you're submitting from. It's going to be held at the Marriott Marquis in San Francisco, new venue. And here's your URL for the CFP. It's open till the 17th. So do make sure that you submit the speakers. The good thing about any conference is that if it has a good sessions, if it has a good speakers, it actually draws a good crowd. So we're depending on the Ray community to share your user journey adopting Ray for the next year. Okay. A couple of announcements. We're actually having our first Ray inaugural European exclusive meeting a month from today. So if you're in Europe and if you have friends in Europe, please join us a month from today. We're going to be talking about Ray Serve and how people in Europe, especially two companies, are actually using Ray Serve and what they're actually doing to build on top of that. So that's going to be our first all exclusive European meetup. It's going to be 8:30 a.m. in Pacific time, which is about 4:30 in East Coast. I mean, it's Central Europe time. Another couple of announcements. If you're new to Ray and this is your first meetup they're actually having, we have various platforms and various avenues that you can actually join the community. So feel free to go to this particular URL and sign up for the platform of choice of engagement. We want to hear from you, and we'd love to hear what your problems are and try to incorporate that in our releases. Okay. Like any other public in-person gathering and virtual event, we are very much steadfast about our code of conduct and civil obedience. And so while I'm not going to read all this to you, the upshot is that we want to make sure that our community gatherings such as this one and conferences are harassment-free. So have a quick read, and I'll leave this up here for about a couple of minutes before we go on to the next part of the presentation. So have a read. Okay, now it's quite customary really towards the end of the year, you know, you see social media being quite suffused with how people have been sort of achieved things in the last year. There's always a reflection about new things they actually finally do in the year. And I thought it was actually fitting for me to recap, some of the accomplishments and some of the achievements that the Ray community, along with the Ray team at Anyscale, have achieved in 2022. So here are some of the high-level achievements at a very high level that I deemed them as pivotal to recount and recap on. And so there are 5 things that I thought were worth mentioning and recounting them, just to get the year started for a review. So one is Ray 2.x or Ray 2.0 along with Ray Air. And these are the 2 milestones. They are kind of related to each other because they really propelled Ray inevitably in the direction that was wanting, it was about to come. And there were 2 things. There's Ray Air and there's Ray 2.0. And Ray 2.0 was sort of built with the principles that we want to make sure it's performant. We want to make sure we simplify the APIs. We want to make sure it's stable. We make sure we provide a lot of debugging and Ray observability tools that make Ray easy to use. And then built on top of that principle, built on top of the stability and reliance is the Ray Air. Now, the question is, what is Ray Air? What is Ray Air runtime? And the nemesis, really, the nemesis of the project really culminated when, over the years, the Ray team has been talking with a lot of infrastructure groups and ML practitioners with groups like Ant and Uber and Shopify and Cruise and OpenAI, which had been at the Ray Summit, that actually used Ray to train the GPT-3 and chat GPT model, which was actually quite useful for us to know, even though they were very secretive, but now they've made it public. To understand what the pain points are, what were the pain points for them while adopting particular Ray? And I think this particular project called Ray A was really a culmination of lessons that we actually learned. And I can articulate those lessons in 2 sort of categories. One was to synthesize these efforts, these painful efforts, to make sure that we incorporate this into the next release of our libraries. And this was to provide a community with what we call a simple toolkit called Ray Air, which is very cohesive. It actually works together. And the second bit was to make sure that we simplify the Ray APIs so that some of the artifacts that these particular libraries, which are part of the Ray Air, work on, whether the input of one can be the output of another one, or something that you actually do a checkpoint on your tuning and training, you can actually use that in serving. And so the APIs are very, very expressive and they're very composable, and that we just make sure that they work uniformly. And the goal were 3 things. One was that make sure we have a unified APIs that ML practitioners can write end-to-end application from data ingestion all the way to serving and scoring. We just make sure that the APIs were simple and intuitive and they're reliable. And more important thing was that we want to make sure that practitioners can actually scale the individual workloads, whether they're doing training or whether they're doing hyperparameter tuning, or whether they're doing serving, batch scoring. Those were actually the important things. So that was really the essence of Ray Air. And if I had to express those pictorially, what I really meant by those 3 things were that if you were a data scientist, or if you're a machine learning and you're using Ray Air, you should be able to scale individual workloads, whether you're just doing data processing by using Ray data to do pre-processing, so you can do your last mile ingestion into your training sets in the distributed manner. The second thing was we want to make sure that if you commit yourself to use Ray Air, that is future-proof. And what I mean by future-proof, what I mean by that is that we want to make sure that out of the box, we support some of the common ML platforms, libraries that most people actually use. And if for some reason, given that the pace at which the technology is changing and the pace at which the ML frameworks are changing, if there's a new extension or TensorFlow, extension of PyTorch, we want to be able to make sure that those APIs are extensible and you can actually use them quite easily without having to wait for another release. So that was the second part of make the Ray extensible and easy to integrate. And the third bit is use the toolkit in a very holistic manner. So if you're actually using, building an ML model, you can actually use it from ingestion all the way to scoring in a very unified manner rather than in a very siloed manner. The problem with our libraries prior to Ray Air, that they were very siloed and they didn't work well together. They weren't very cohesive. So the idea about Ray Air using Ray 2.0 APIs made us easy to sort of use the artifacts that can be used from one to the other. So that was, the reason behind it. And if I could, bear with me with this marquee architecture slide, if I could use that as a layered kickoff functionality, you got Ray Core sitting at the bottom, running on top of your common cloud. And as you go up, you got these cohesive libraries that actually work together. And then if you go up at the top, you actually have all these integration points. Some of them are maintained by the community and others come straight out of the box. So you can actually use Ray Air to do your end-to-end application. And that's sort of the vertical layer of functionality. And if I were to sort of look at it from a horizontal point of view, out of the box, Ray Air comes with these common frameworks that you actually use. And because the Ray Air APIs, the base APIs for trainers and tuners are extensible, you can actually extend those classes and incorporate the new ones. And finally, if you have customizable components that you want to use, let's say you want to use data store that you want to read from MongoDB, or you want to use from Delta Lake, or you want to use Snowflake, you can actually write the extensions to read data and use Ray data sets. So that primarily is one of the things that Ray Air actually accomplishes. That, and obviously it's actually built on top of Ray 2.0, which was a massive achievement for us to get that going. As I say, Ray Air is one of the things that was built on top of that. Another monumental thing that actually was quite important was the introduction of Ray datasets, and the work that actually started towards the end of 2022 was where we were able to actually shuffle 100 terabytes of data using Ray data. Now, shuffling when you're actually doing training is a quite important part, because when you're doing distributed training and when you're doing epoch per shuffling, you want to be able to make sure that your data is well randomly distributed. So shuffling is an important part of an operation, and Ray dataset was able to actually do that. And the other thing, the efforts that started in 2002 led yesterday, where we actually published our first world record that we actually set, which was the cloud store benchmark that we actually achieved. The last record was actually set in 2016, and I recall it quite vividly because I was at Databricks at that time. And in 2016, we actually released this particular cloud mark. And it actually shifted the perception of people. It shifted the perception of how people actually looked at Spark at that time, rather than looking at a research project that emerged out of UC Berkeley from the AMP lab at that time. AMP stood for Algorithm, Machines, and People, into the real world, where people started seeing that Spark is here for us to actually use at scale, both in production and use cases. And that was a milestone for Spark in 2016. Fast forward, 10 years ahead, we set the record yesterday as being the most performant and most cost-effective way to actually use Ray. And this again sets a milestone for us to the people who are actually using Ray with serious use cases in production. That Ray is not only a research project that emerged out of Rice Lab, which was a success to the AMP Lab. It is not only an academic exercise for researchers, but it is actually a product that's actually being used by industry, and we'll see some of those people who are actually using it. Another thing that emerged out of KubeRay, another thing that emerged out of 2.0 was the KubeRay, which is a toolkit for Ray to run on Kubernetes, and this is in beta, and it's a replacement for the old Python-based version of the operator. I think one of the writers of the contributors to KubeRay, Dimitri, is on call at the meetup. So thanks a lot, Dimitri, and the group that you actually work with. And the other bit was the Ray Serves Deployment Graph APIs. Now, those of you who actually have worked on deploying models, you do realize that models in deployment or models in production don't exist in isolation. What I mean by they don't exist in isolation is that models are work together. They're ensembles of model. You might be doing some inference in the input that actually comes in, which is going to be predicting something that might be used as an input for the second model. So you might have a chain of model, you might have an ensemble of models. And these deployment inference graphs allows you to create a graph of all these different models that you actually do, and they can be linked together and be used as an inference graph. And that way you can actually deploy that as a single unit of execution. And each and individual models that you actually have can be scaled as replicas in the particular graph. So if certain part of the model that requires more traffic, you can actually you can have more CPUs, you can have more GPUs, or you can actually have more resources dedicated to that, so traffic can actually goes to that. So that has been sort of a huge improvement in 2.0. And based on 2.0, Ray Air was actually built on top of that to solidify that. So if you want to try it out, pip install Ray default and have a go with it. The second bit that actually started that I think it's worth mentioning is it's one thing really for Ray to be able to easily make you write distributed application. It is a whole different ball game if you have to debug something, right? If you really don't know what's going on, if you have to scour through the blogs and you have to figure out, what the hell is going on? Why my resources are sluggish? So we had to introduce this whole idea about Ray Observability, which is actually started in Ray 2.0, and it's continuing to progress in 2.1 and 2.2. And last month, we actually had our first part of the meetup where we had people from the Ray core team talk about all these particular metrics. And we have given people the ability through this very visual real-time metrics of all the resources that your Ray tasks are using, that your Ray actors are using, how much memory they're using, CPU, GPU, heap memory. You got all this actually happening in real time. So you can actually zoom in into those particular metrics. You can go into a particular task, you can go into a particular actor, you can particularly go into what part of the node is actually using memory. And this has been a huge, huge monumental improvement in the 2.x series. And today you're going to hear about how the OOM monitor that Clarence is going to talk about, which is part of this continual effort that we started in 2022, and we're continuing as part of our principles to make sure the Ray 2.0 is stable, its performance is reliant. Number 3, structured documentation. Now I'm going to repeat something over here. I'm going to declare my tenet. Good code begets good documentation. Good code begets good documentation. If you agree with me, put a thumbs up. If you disagree with me, put the thumbs down. I'm okay. But good documentation always begets good code always begets good documentation. Those of you who actually have been working on the open source projects will appreciate immensely if your documentation was complete and comprehensive, if your documentation was discoverable and searchable. You type in something and it gives you a list of things. If your documentation was suffused or was replete with examples and code snippets and user guides and good runnable code that you can actually take it in a notebook and then run it as an example and take some of the code and use it for your use cases, those are immensely valuable for you as a programmer to get your productivity up. And if the documentation is well organized, is well structured, there is a nice TOC, it's easy to navigate, and it's quite intuitive. And those are high standards. Those are high standards of metrics to actually achieve. And one of the efforts that started in 2.0, and it continues to do that, is to make sure that the documentation is consumable. And just like any good writing, just like any other good code, it's never complete, right? Documentation is never complete. It doesn't stand on its own as a finished product. There's always room for improvement. And we are steadfast in our belief and in our commitment, in our conviction to make sure that this continues in our efforts. And if you look at some of the documentation that has improved since the early releases, you got a gallery of user guides that actually attack each and every different workload that tell you how to actually use it. Both for each and every component, we have user guides, we have examples. The code snippets are replete with, the APIs are replete with runnable code examples that actually explain and illustrate how you can actually use that particular API. So that's the third bit. Now, whenever you reflect back some of the times that Ray actually has gone through, you tend to look at early days with a soft sentiment of nostalgia. And here we got Robert and Philip, the original creators of Ray and co-founders of Anyscale, giving their first presentation at the AI conference. I think this was around 2000, either late 2017 or circa early 2018. And on the right, you got Richard Liu, who was one of the first contributors, talking about Ray Tune and RLlib. We didn't have any other libraries. Those were one of the first few libraries that Ray started with. And so we have come a long way. We have come a long way from the early days of Ray to today. And it's quite heartening to see how the community has actually gone. The fourth and the fifth bit is the Ray community and the Ray Summit. And we have seen meetups in far corners of the world, from Medellin, Colombia, to all the way in Toronto. I was in Toronto at the MLOps conference doing a tutorial on Ray Serve and Ray. And there were 3 other talks on Ray, which were completely not from Anyscale. And I was quite heartening. One of them was from Shopify, Isaac, who actually gave a talk about how they actually use Merlin And I was in New York at the Pi Data doing a tutorial, and there were 6 different talks from Ray, and not from Anyscale. These were from the community, and it was quite heartening actually to go to a particular conference and realizing that there are other people talking about Ray, and that really is a testament that Ray is actually really taking off in various ways. And here is some of the companies who are actually using Ray at a massive scale, right? And all these companies actually presented at the Ray Summit how their use cases are actually being used, what scale they're actually using, what part of Ray they're actually using. And some of the stats that you actually have at the bottom are really vanity stats. I agree, you can actually make a case of that. But I think those are important signals, I would contend. These are important signals for you to understand how popular your source is, how many GitHub stars you actually have. But important thing is how many contributors you actually have, which is really a good indicator of the adoption of Ray. We have about 770 contributors who have started just in the last 3 or 4 years. 5,000 different repositories depend on Ray. They have include statements in Ray that allow that. Over 1,000 plus organizations are using Ray. All these little things actually add up. The power of small things is enormous when you actually look at them in collectively. And if I were to compare those in terms of the activities actually happening on GitHub, let's say compared to tasks, we actually see that Ray is really taking off in its popularity. And if I were to compare that with the common distributed system we actually see today, Ray kind of matches them, or it also sort of beginning to approach them in terms of how Ray is being popular. So these are actually good indications that in the last couple of years, starting from 2022, we're beginning to see more emergence of Ray. And the community is an important part. You guys play a huge role in advocating Ray and being part of the community. And I think communities, growing communities, create values. And what I mean by value is that they create assets, they create blogs, they talk at conferences, they share their vision. These are important part of how community actually creates value. These 2 books were actually written in 2022 and they've submitted for publication. One from the community. Holden Karau is a big advocate of open source project. Some of you actually might know her, she's Canadian. And Learning Ray is another book that was written by the Ray team, which is now available. I think it might be available in a couple of months, but the Scaling with Python is available today through pre-order. So these are the assets that the community actually creates and the blogs that people are actually writing. And last but not least, Ray Summit, I don't know how many of you attended. If you attended, put your thumbs up. It was a huge bloody success. I mean, he had exceeded our expectations. It exceeded not only the caliber of the keynotes, but also the sessions and the training session that we actually had. But the energy, the camaraderie, that comes with when you actually go to an open source conference. You meet people from around the globe that you've interacted with them with the Slack. You meet people and have a chat with them that you've communicated that on the social media. You meet with the people with whom you actually either worked on the PR and have a pint, and have a laugh with them. And these are priceless moments at any open source gathering that you actually have. And we're planning to actually repeat that in 2023, coming up in a few months. So hope to actually see you there. So enough of this recounting and enough of the nostalgia. I'm going to now hand it over to Clarence to start our first talk. So Clarence, go for it. Clarence is a software engineer with the Ray team, specializing on Ray observability and Ray stability and core. And he's going to talk about the second bit of our Ray core, which is the monitor. So go ahead, Clarence.
Yeah, thanks, Jules, for the introduction. So maybe just give me a second. I'll try to.
Sure.
All right. Yeah, thanks for the patience. And again, I'm Clarence. I'm a software engineer at Anyscale working on Ray core. As you probably know, Ray core is the part of Ray that provides the basic primitives like tasks, actors, and objects. Today, I wanted to share the recent work on the Ray memory monitor, or AKA the killer. So it monitors the memory usage on the node, and when the node usage exceeds a certain threshold, it'll try to free up memory by killing a task. So this feature is already enabled by default in the latest Ray release, which is Ray 2.2 plus, and it is built to improve the stability of Ray. So just to very quickly go over the agenda. So we'll first give a very brief introduction to the memory issues that someone may encounter when they're using Ray. And then why the existing solution does not work well, and how the Ray memory monitor might help. After that, we will go give an overview of how the memory monitor works. We will deep dive into the task preemption policy that is used to decide what tasks to kill in order to reclaim memory. Finally, we will also walk through some demos to see the memory monitor in action. So one of the key values of Ray is that it can help us effortlessly scale our workload. So here we have a workload that, let's say we need to run a bunch of tasks. Say we want to process a bunch of images where each task processes a subset of those images. And we want to do it, obviously, as quick as possible and the most efficient as possible. So in this example, right, we use Ray to distribute a bunch of tasks across a cluster of 3 nodes, where each node has 4 CPU. And in this example, each task is requesting 1 CPU. So based on that, we can see that each node would have 4 tasks running. So, but what if the 4 tasks combined, consumes too much memory that it causes the node to run out of memory? So when the node runs out of memory, which in this case includes the swap space, so on Linux, this will trigger the OS killer, which will pick a process and to kill and free up the memory so that it'll give some room to the kernel and other processes that are running. So now back to the second part, right? So if there's already a killer, in the operating system, why do we still need to build one inside Ray, at the application level? So before we answer that, to recap, right, the OS killer triggers when the host or the node runs out of free memory pages. And when that happens, it'll prioritize killing memory-hungry processes first. The frequency of that also happens is also limited, meaning that it is still possible for a node to be in a state where it is running out of memory and a bunch of processes are stalled waiting for memory to be allocated. So what we've seen in the past is that when this happens, the node and the Ray itself freezes and it becomes unresponsive. So in addition to prioritizing memory-hungry processes, right, the OS killer calculates a score for each process and uses that to determine which process to kill. There are configurations that allow certain processes to be marked as higher priority so that it is less likely to be killed when the killer triggers. So Ray by default configures its processes so that the tasks and actors are more likely to be killed before it goes and kills other critical processes like the Raylet, GCS, the agents, dashboards, things like that. So there are a couple of issues as we will go into with why the OS killer is not sufficient. As stated before, it is possible that the node can stall, right, when the tasks are very aggressive at consuming memory. And when Ray stalls on the node, it becomes unresponsive. What we have seen is that the node can sometimes stall for over half a minute. And that would trigger the health check to fail. So when Ray fails the health check, the node, it assumes it is dead and then it will remove it from the cluster. Another situation that could happen is that other critical processes like the Ray dashboard agents, it'll stall, won't be functioning. So here we have a screenshot of a workload that is running using the OOM killer. And these are diagrams of the Ray dashboard. So this is showing a workload that's running on a single node cluster that's having memory issues. So on the right diagram, the green diagram, it shows that the memory usage of the node, and that the dashed line is indicating the max node memory. What we're seeing here is that the usage is running very close to the limit, and it's very likely that it is running out of memory or ooming. And on the left, we can see the number of tasks that are running in the cluster, broken down by their states. What we see here are gaps in the metrics, all right, that is being rendered by the Ray dashboard. So when the node is running out of memory, the processes stall, and in this case, the metrics collection is failing to record the metrics, and therefore it produces these gaps when the dashboard tries to render. And one last thing to note in the diagram to the left is that the number of tasks that are running, it stays relatively flat. So now we're going to look at the same dashboard and for the same workload, but after we turn on the Ray memory monitor. What we're seeing here is that there are hardly any gaps and that there's very little to no stalling on the node. We also can see that there's also a peak in the number of tasks that are running, which shows that the node is actually being responsive and the tasks are being scheduled. So another problem with relying on the OOM killer on the operating system is that it is possible for tasks to be thrashing. So let's recall that the OOM killer, right, it prioritizes killing processes that use the most memory. So to illustrate thrashing, here we have an example with two identical tasks that needs to run, where we assume the memory usage of the task is increasing monotonically. So the left task here, it got scheduled first and it's running at 90% of its intended memory usage. It's almost about to finish. Whereas the right task here, it just got scheduled, started running, and it's only using about 30% of what it needs to use. So let's assume at this time the node runs out of memory, the OOM killer kicks in. It is more likely that the task on the left that got scheduled first and is about to finish is the one that is being chosen and killed by the OOM killer. So let's say we kill the task that was about to finish. So now that the task is killed, right, Ray will detect that the process was gone, and it'll try to reschedule and rerun that same task. So now let's say that the task that was not killed before, it keeps making progress. It's almost done. Now it's using 90% of its memory. But at this moment, it is possible that the node is running out of memory again, and it just might repeat what just happened, which is it will try to kill the task that ran first that was about to finish. So in short, with the OOM killer, it is possible for a task to thrash where it is more likely to kill tasks that are almost finished. But ideally, what we want to do is to minimize wasted work, right? And in this case, perhaps it should kill the task that was newer, that has made less progress. Another disadvantage of relying on the OOM killer is that there's a lack of visibility when something is going wrong. So for example, here we have a single task that is leaking memory. It's causing the node, right, to run out of memory. It'll be killed by the OOM killer. So in this case, let's say the task is configured to just, retry forever. And what will happen is that the task, because it's running out of memory always, it'll just keep retrying and failing, and it'll appear to be hanging from the user's perspective. And someone at that point would then have to go and debug why the task is hanging, right? Why does it keep failing forever? So ideally, Ray should be able to detect this condition and fail and produce some useful message to indicate that there's something going wrong. So to quickly summarize, right, the OOM killer doesn't work really well because the nodes could stall, tasks could be crashing, or just hang. So here we will briefly go over how the Ray memory monitor works and how it fits into the Ray architecture. The memory monitor is part of the Raylet, which manages a bunch of tasks or actors, each belonging to its process. The process publishes stats like the memory usage to the operating system, and the memory monitor will periodically pull the memory usage from the operating system to determine the memory utilization on the node, which would include non-Ray processes, the Ray object store, and also obviously the heap usage of the tasking actors. So let's say the memory monitor reads the memory usage. If the combined memory usage is above some threshold, let's say 95%, then it will then look for a task or actor to kill. So here the memory monitor applies some kind of policy to determine what or which task to kill. And then it goes and kill it. So after it is killed, the same process repeats. If it detects that the memory usage is still above the threshold after killing the previous one, it will trigger and kill the second one. So when the node runs out of memory and Ray needs to kill a task, we apply the preemption policy. And so now we're talking about what policy does Ray use to choose the task to kill when the node is running out of memory. So we think that the ideal policy is one where it would fail if the workload cannot complete, and notify and provide some useful information on how it could be fixed to simplify debugging. We also expect parallel tasks to run in some degraded mode when the node is running out of memory. It may run slightly slower than if the tasks were to run serially, but the workload should still complete without failing, and it shouldn't be stuck or hanging. So in the latest release of Ray, which is Ray 2.2, the Ray memory monitor is enabled by default. And the preemption policy that is using to find a task to kill is fairly straightforward. So it'll prefer killing a task that is retriable, because if the application specifies the task is retriable, then the system would know that it is safe to retry this task. So we will prefer killing a task that is retriable. And within those tasks that are retriable, it will find the newest executed task to minimize thrashing. So in Ray, right, a task by default is retried up to 3 times, say if it crashes due to an error in the system. So when a task is set to be retriable, the memory monitor will prioritize on killing it, as it knows it could be safe to be re-executed later. And by default, an actor is not retriable, and therefore, by default, the memory monitor will prioritize killing tasks over actor. And then the memory monitor will then sort these tasks by its execution start time, and then it picks the last one that started executing. As we said before, it'll help minimize wasted work. So to illustrate this policy in action, we'll use a real workload. In this case, hyperparameter tuning. Here, we run 2 trials in parallel to tune let's say a machine learning model using Ray Air. And to recap, right, Air stands for AI Runtime, which is the Ray toolkit for ML applications. Each trial here is training the same model, but on different parameters. And Ray will help us schedule this onto a single node cluster. So in this diagram, the driver script first creates the trial actor, which is then used to coordinate the execution of the entire trial. The trial actor then spawns a bunch of data tasks that will pre-process the data, where the results are then stored into the Ray object store. The trial actor also spawns the trainer or the training actor, which reads the data that was produced by the data tasks in order to train the model. So now let's say we are running this workload on a single node and the node is running out of memory. According to the preemption policy, right, we'll first prioritize killing a task. So the data tasks that are pre-processing data are highlighted as one of them that will be killed here. Among the data tasks, we then pick the one that was last executed. So let's say the one to the right was the last one, then the policy will go and kill that. So one of the problem with this policy is that it may lead to starvation. So it is possible that a trial can get stuck where all of the data tasks are preempted in favor of a different trial, as shown in this diagram. The trial on the right side has no data pre-processing tasks to make progress. Ideally, we would keep some tasks in each execution branch to avoid this situation. Another problem with this policy is that it cannot detect when a task is hanging because it is using too much memory. So if the task is set here to be, retrying forever, it will appear as if the task is hanging and it never completes because it just keeps running out of memory and then it just retries again. So in Ray 2.3, the upcoming release, we are making some improvements to how the task is being selected. The key change is that now we would group the tasks from the same parent together, which we'll illustrate. And then try to kill the largest group to ensure liveness. So let's go back to the same workload that we do hyperparameter tuning, but using the new policy. Like before, right, the actors are last to be killed. So we form, it's a group that is only for actors that are highlighted here in purple. And then we also form a group for each parent. So from this example, we can see that there's a group on the left that contains the data tasks for the left trial. And then the same thing, there's another group of data tasks for the right trial. So based on the new policy, it creates 3 different groups. So when the node is running out of memory, it'll pick the largest group. So in this case, it'll just pick the left group, and it kills one of the tasks. So let's assume the node is still running out of memory. Then the process repeats. It picks the group, the largest group. So in this case, the data group on the right is larger than the data group on the left, so it kills a task on the right group. So now you have 2 in each of the data groups. So let's say the process keeps continuing. If the node is still running low on memory, after a certain point, there's only 1 task left for each of the trials. So now, let's say the node is still running out of memory, right? Then, well, it will have to kill, in this case, it will decide to kill a data task in the left group. And the preemption policy, right, the new one in 2.3, it states that it'll throw an error if it kills the last task of a group. So in this case, it kills the last data task of the left child. And what will happen is that it will then throw an error and provide some message indicating that the workload ran out of memory, and also provide some more information on how to fix the problem. And the solution here, when we talk about resolving or fixing the problem, is to either increase the memory capacity in the node, add more nodes, or just reduce the parallelism so that there are fewer trials running in parallel. So going back to the previous example where there's a task that's running and leaking memory and running forever because of the infinite retry and hanging. So with the new policy, it'll see that this is the last task of the group, and it'll just fail immediately instead of hanging. So now I'll quickly go into the demo where we show the memory monitor that is running. So the first thing I'll show here is the second example we just talked about, which is we have a single task that is leaking memory, but is retrying infinitely and hanging. So here we can see that it sets the retry of the task to be a -1, which means that this task will just keep retrying forever if it's crashing. And so what we see here is that now I just run the script, so it'll take some time to run. We can come back to this afterwards. And then the other demo, what I was going to show is that we'll have the hyperparameter tuning workload. So here I have actually two more demos environments. Here I'm actually using the Anyscale workspace, which gives me the IDE direct access to the cluster. So here what I did is I created an environment and then I cloned it. So create an identical environment so that we can just do like an A/B comparison. So the two things that we're comparing here is hyperparameter tuning with one trial. As you can see here, it says 2 trials here that's running parallel, and then the other cluster is running a single trial. It's kind of so it takes a couple minutes to run these things. So I'll just run them, and you might be able to see the results. But if not, I'll show you the results from the previous one. So let's say going back to the infinite retry task, so we can see if it's finished. Looks like it's already finished here. You can see that instead of running forever because of the max retry that's set to infinite, it actually fails right away. The program already finished with an out of memory error here. It also prints out the offending processes that is using too much memory. So in this case, the leaker task that I just wrote above is using 16 gig memory, and then it got killed. Also here it shows a link to our documentation, which describes how it may help resolve the issue. So I already opened it here. So it has a page containing some information about memory monitor and kind of describes how it can be fixed. So in this case, it would suggest maybe increasing the memory capacity of the node, or just reducing the concurrency. But in this case, because the script is designed to be a bad task, so it probably won't help. But if it's a normal task, those suggestions should help a little bit. I would assume these are still running. So maybe we can just look at some of the one of my previous runs. here. So the trial with a or the cluster of a single trial, it took about 8 minutes to run. And then we look at the cluster that was running 2 trials in parallel. It took about 13 minutes. So actually, it was actually faster to run them in parallel. And then with the Anyscale workspace, I'm also using it to access the Ray dashboard in Grafana. So we can see like what was actually happening to the workload. So now I'm in the Ray dashboard for the cluster that was running 2 concurrent trials, and you can see that, well, first of all, like the memory usage is kind of flat, which indicates that it is being the memory monitor is doing some work to prevent it from going above 20 gig around, and then eventually finishes the workload. And then if we look at the tasks that are running, we can see the big purple at the very bottom is the number of running tasks at any given time. So you can kind of see that at the beginning it tries to run a bunch of tasks, and then they get killed and then get restarted, but it smears out a little bit because the OOM killer would try to do some exponential back off to reduce some of the pressure. So that's why you see it's not that aggressive over time. Another thing to look at is using the Grafana dashboard that is available on Anyscale is to look at the counter. So this records like the instance of how many times the OOM killer went in to kill a task. So you can see like it triggered about 100 times. And then if we go compare it with the cluster that ran a single trial, it actually also has some auto memory. So I guess it's around 49. So you can kind of see that even though when we were running in the 2 trials in parallel, the amount of preemption was not as bad as if we were to try to run them together. So this concludes the demo. So I'm going to go back to our slides. So just a very quick recap, of what we talked about. So in Ray 2.2 and above, the Ray memory monitor is enabled by default, and it's helping us to improve the cluster stability. It also has some improved observability in terms of logging dashboards. And then in the upcoming release, we also have some tweaks to the algorithm to make it even more robust. So that concludes my talk about the Ray memory monitor. Now I'll hand this back to Jules.
Well, thanks a lot, Clarence, for that insightful observability lens through which we actually prevent and understand what's actually happening behind the scenes. If you guys have any questions for Clarence, please put it in the Q&A. But Clarence, while you were mentioning about, when you were talking about things, few things kind of popped into my mind as you were going about doing that. You mentioned there is a certain threshold when the OOM killer starts looking at it. What is that particular threshold? You said it's enabled by default, but how does someone go about and change it? Is it something that is pre-configured when you run 2.2, or can you actually tweak it to make it higher, to make it lower?
Yeah, no, that's a great question. So yeah, by default, it looks at the node memory or the container memory, and if it's above 95%, then it'll trigger and start preempting tasks. There's a environment variable that can be set to adjust that number, and there's our documentation page contains those details on how to do that.
Now, is that 90% or whatever the threshold, is that collectively across the entire cluster, or is it per node?
Yes, that's a good question. Yeah, it's per node. So one example of one of our users is they would like to have a higher threshold for their worker nodes. So they were able to do that just by setting the environment variable differently.
Now, there are a couple of times you actually use the word tribal and non-tribal, right? Certain tasks which are tribal and certain tasks which are non-tribal. Could you explain what's the difference between what's tribal and what's non-tribal, and what determines one is one versus the other?
Yeah. So for task and actors, so by default, tasks are retriable, meaning that if it, for some reason, it crashes, right? Or, for, let's say, if it's running on a node, that node disappears, it failed. So the task would be retried, resubmitted, into the cluster. And by default, actors, they don't retry. And so they both have options or configurations that you can adjust the retry count just through the Python annotation. You can do that.
And we actually have a question from Rajiv. He's answering. Great work. Well, thanks a lot, Rajiv. Thanks a lot, Clarence and the team. As a Ray developer, should we or can we change the way we develop and design applications to better leverage the new Ray OOM killer? In other words, do they actually have to change the behavior? Do they actually have to adopt certain strategies to take advantage of this? Or the OOM killer with the thresholds they actually maintains give them a good starting point, and they can start tuning the parameters to do that. So what would be your advice? How would they actually take advantage of the OOM killer?
Yeah, I think like the OOM killer, it's on by default, so like someone wouldn't have to like go and try to look at it. I mean, and I think the best way to observe is when, if the workload is running, it maybe is skewed and it's triggering a lot of memory issues. Now, before this memory monitor, like we don't even know why it, like the task crashed. Now it will actually print the error message. It'll print like this is actually happening because of memory issue. Now we have like dashboards Grafana like to tell us this is actually happening. So I think when these situation happens, which typically, if hopefully it doesn't always happen, and it depends on the workload, then it's a good way is to look at like how to resolve it. For example, at that point, like maybe maybe it should reduce the concurrency, or maybe it needs a node that has the higher memory ratio because of the nature of the workload at that point. So I think it helps make it simpler to debug and find these issues. Mm-hmm. Whereas before, it's like a shot in the dark. We don't even know like, okay, so this is a memory ratio problem, or whether there's other things going on.
Now, when you were actually showing that offensive task that was just too hungry to take all the memory off the heap and immediately actually failed with the OOM killer, where you actually say this is memory function that actually happened. Now, suppose I'm a developer and I'm doing the second bit, which was doing my hyperparameter tuning and doing all these trials, but I'm not going to sit there, right? I'm going to launch the particular job, and I'm going to go out for a cup of coffee and come back. And obviously, I'm not watching the events, or I'm not watching the dashboard. So I come after 2 hours, and all of a sudden, everything is finished, or this thing has been killed. I go to the dashboard, and time has gone by because 2 hours has gone by. How and where are events or actions that the OOM killer recorded that I can actually look back? Is it recorded in the logs somewhere? Yeah,
the quickest and easiest way is to go to the Grafana endpoint. So in this case, I'm assuming that like someone deployed Ray, and then they also connected their monitoring stack with like Grafana, for example, and then because we actually emit those counters, like so we have a cluster-wide counter of how many OOM events has triggered. Mm-hmm. That will be the quickest way to see, let's say I finish a workload, it's slower than what I would expect. It could be because, I'm suspect that it's, because there's a lot of, out of memory issues. So that would be a very quick way to look, okay, is there the line change like going up? And so that, if that case, then that would indicate there's an issue. And then the documentation would be a good place to go to like look at how to, resolve or reduce that in order to run the workload faster.
Now, if I was an MLOps guy, and I would be begging the question, how can I be notified about the OOM killer taking a lot of actions, right? I know that it's not on our roadmap where I want to be able to be notified. And I think this is something that when people do have large jobs that actually run over a time, where you're doing, distributed training for large data sets, computer vision, it does take a lot, and they take a lot of memory intensors. Or if you're actually doing a huge hyperparameter sweep over a large space, this is going to take a long time. And obviously there are going to be some OOM events that actually kill. But I do want to be notified. What do you think is the best way for people to approach that?
Yeah, I mean, definitely like we can extend the metrics. So I mean, if it's already connected to Grafana, I mean, it's just adding alarms now at that point, right? If there's excessive issue happening, will obviously slow down the workload. Then like, or maybe it's just slightly misconfigured. Then in that case, then setting an alarm just to measure the the growth of that counter would help detect.
And these OOM killer events, the actions that the OOM killer take, those are considered as Ray events, right? So we also, if you go to the events page, you will actually see a history of all the events that happen, just like the autoscaler, loads and brings down a particular node. Likewise, you would actually have these events being part of the node. So you can actually also look at that as a story of how the OOM killer reacted.
Exactly. So that's part of the metrics emission that we're showing earlier. Like that line is the same metrics reporting mechanism that we are using to report all the other metrics in Ray.
Okay, well, I think we don't have any more questions, and I don't want to be hogging the mic for too long because we have Kshetrajna, who's actually waiting in patiently to tell us all about how they're actually using Ray at Shopify. So, Kshetrajna, thanks a lot for taking the time to come from Shopify. Tell us how you guys are actually using it. So, take it away, and Clarence, just stay on. If some questions come up in the Q&A, feel free to answer them.
Yeah, thank you.
Thanks, Jules. Can everyone hear me?
Yes.
Perfect. All right, let me share screen. So, can people see my screen? Awesome. So first of all, hello everyone. My name is Kshetrajna. It's not an easy name to pronounce. Most people at Shopify call me K. So I'm very excited to be here today to talk about some of the work that we're doing over at Shopify. And so for those of you who are not familiar with Shopify, we're a leading global commerce company. We provide trusted tools to start, grow, manage, and market a retail business of any size. Our goal is to make commerce better for everyone with platforms and services that are engineered for reliability, while delivering better shopping experience for consumers everywhere, right? Shopify powers over 2 billion businesses. The last time we publicly announced that across 175 countries. And I'm not going to list all of the various brands we power, but almost everyone would have at some point in time purchased something from a Shopify merchant, whether you realized it or not. In most cases, you probably didn't realize it, and that's by design, because we consider ourselves almost like the OS of commerce, and so we stay in the background, right? So within Shopify, I specifically today work for a team called Capital. But what I'm going to talk to you about today is some work that I did with a different team at Shopify called Commerce Algorithms, where we essentially built something we call the Product Understanding Engine. What that basically means is we built an ML application to extract structured metadata around products that are inherently the data we get for products are unstructured in nature, right? So that's the topic, and we're going to talk about how we built it and what kind of infrastructure, and Ray is a big part of that, that enabled us to do it at the scale that we needed to be done, right? So having said all of that, I wanted to quickly go over some of the areas that I'll be discussing today. I've tried to touch over a lot of different components of the system, and I would be more than happy at the end of this presentation to dig deeper into specific areas or components as interest pops up. We'll start by discussing what product understanding itself means at Shopify and why we think it's important for our merchant success. Once that is defined and understood, I'll talk to you about the way we formulated this as a machine learning problem and the specific modeling techniques that we took to solve this problem. I'll then go over some of the scaling requirements, and this is where Ray and our ML platform comes into the picture, and what the infrastructure is that we had to build to support this. And then finally, we'll talk about the most fun part of this project for me, which is how we surfaced up all of this to our merchants, who are our end customers, and then kind of build workflows that help our merchants and how this actually makes a difference in the real world, right? And then finally, we'll talk about where this is going to go from here. Right? So what is product understanding, right? Essentially, we want, like, I'll let you read what's on the screen, but essentially we want to build a service that extracts useful metadata around products, right? Our merchants are selling millions and billions of products, in fact, right? We have millions of merchants selling billions of products, and they upload all sorts of information about the product that they're selling, right? But we need a structured way in order to understand what our merchants are selling, right? And the usage of this can be from anywhere from internal teams who are using these predictions for various analytical purposes, all the way through external partners like Google, Facebook, TikTok, in order to kind of do things like search and relevancy, trust and safety, legal, tax purposes. There's so many other unique consumers we have of this product that it just touches every aspect of commerce, right? Having structured metadata around products basically is a prerequisite to do commerce well, right? But you can very justifiably now ask me at this point, why do you need machine learning to do this, right? Why can't we just collect structured metadata just like we collect everything else from our merchants? And that would be a great question, right? So let's actually take a trip down memory lane, right? I don't know how many of the people in the call today have used Shopify before, but the screen you see in front of you would have been very familiar if you used Shopify a year ago, right? This is basically the product admin page at Shopify. This is where merchants would have come about a year ago, and they would have tried to update their products, right? In this instance, I'm going to try to create a product. I'm selling a dog bed, and those are my dogs that you see in front of you, right? And I'm going to use their help to market this product. As a merchant, I have a lot of flexibility here to add fields that are useful to me, right? I can add titles, descriptions, vendors, product type, collections tags, all sorts of things, right? But notice that none of this is structured. Like, I can put any free text I want in any of those fields. I can add an image if I want. I can add multiple images if I want, right? But none of this is structured in any way, shape, or form, right? It's all unstructured data. What our merchants do is they normally use all of these fields to organize their products and catalog internally, right? It's super important to realize that the way every merchant organizes their store is very different, and it's almost unique in a way to them. And so it doesn't really work, right? So take for example, that field there that's called product type, right? I have just added there that it's called my custom dog bed, right? If Jules was selling the same thing, he would probably call it super duper bed or something. Like, it could be called anything you want. It's completely free text, right? So that doesn't really help us do metadata extraction very well. We need to have a better way in order to kind of extract metadata from our products from this very unstructured world that our merchants are operating in, right? So this creates a problem, right? Because fundamentally, we are not understanding what our merchants are selling. And partners like Facebook and Google rely heavily on these kind of information, not just for organizing their catalogs in their shopping ecosystem, but also things like search and relevancy. In fact, there are legal ramifications to this. We have to, for example, taxation is handled differently based on what you're selling, right? If you're selling food, I need to tax you differently than if you were selling heavy machinery, right? So it becomes very critical for us to kind of know what the merchants are selling and more structured data, right? So that's the problem, right? We have to go from this world where our merchants are giving us unstructured data in a world where it's local to them to something that's more global and standardized across all merchants, right? So what do I actually mean by that? Let's go back to that same dog bed that I was trying to sell, and let's look at it, right? What kind of metadata could we extract from this? Well, I can tell you that it's a dog bed immediately. That's the category of this product. It's a dog bed. I know that its color is gray. I know that it's the memory of like the fill material of it is memory foam and so on and so forth, right? There's many, many attributes that I can now extract for that image, right? A lot of us are very familiar with all of these different attributes because we use them all the time when we do online shopping, right? Whether it's through search or whether it's through filters, we use all of this to get relevant results. And these attributes are going to help us define and organize products. The key thing to remember here, of course, is that all of those values you see, whether it's a dog bed, whether it's gray, all of those are coming from a controlled list of finite values, right? As an example, the shape of my dog bed can possibly only take one of three, let's say, right? Oval, rectangular, and semicircular. There are no other values that it can take. It is coming from a controlled list of categories that can go in, right? So having said all of this, the focus of the rest of this discussion is going to be narrowed down to just one of those attributes, which is category, and how we built an ML model using Ray and Tensorflow to predict product category. So with that all said, let's focus on the specific task which our initial model was for, right? Like I mentioned, we wanted to infer the product category for all products that our merchants are selling. In reality, this problem is twofold, right? First, we need to come up with a taxonomy or a controlled list of products. We did a quick count. We went to our database and we're like, hey, we have that product category that our merchants are putting free text for. Let's look at how many unique categories there are. A quick count of that showed us millions and millions of product categories. No, that's not sustainable. Like we cannot have millions of categories. It needs to be more controlled. It needs to be something that we can actually use, right? So we needed to come up with a taxonomy of product categories that are manageable and useful, right? Let's say we did that. Then I need a machine learning service to help me categorize each product. And remember, our merchants are selling billions of products with multiple tens of billions of images, to categorize every one of them into one of these categories, and then kind of go from there with all our downstream consumers. So to solve the first problem, which is how do I come up with the taxonomy? Well, we didn't, right? We said, this is not a problem that we want to solve by ourselves. Let's see if somebody else has solved it for us. Luckily, there exists something called the Google Product Taxonomy. This is open source. It's maintained by Google, of course, as the name suggests. And you will immediately notice that this isn't a flat list, right? Rather, it ended up being a hierarchical tree-like structure, right? What that means is you'll see that on the top level there, the first thing you see is animals and pet supplies. Now, within animals and pet supplies, you see two separate subcategories, right? Live animals and then pet supplies. And this goes on and on, right? So and this makes a lot of sense if you actually think about it, right? Because what I'm wearing is a t-shirt, but it also belongs to the clothing industry, right? And there's probably specific types of t-shirts, and you can go more and more granular, right? And maybe different use cases want classifications at different levels, right? So maybe I want to report on revenue growth across the top level industries, right? Or maybe I want to go a little deeper and say, hey, just show me the revenue of the clothing vertical, right? Or maybe I want to go super granular and say, hey, is this person likely to buy dog food versus cat food, right? So we have the need to go down to different levels of the taxonomy for different use cases, right? And so it's important for our model to be able to predict across those different levels, right? So here's an example of one single branch of the Google Product Taxonomy, right? So you start all the way up there. I believe it starts off at arts and entertainment. And then if you come down all the way to the left, it'll probably end somewhere with clarinet care kits. Like that's how granular this thing gets. There are over 6,000 nodes in this tree, right? And so every product can belong to one of these branches, right? So essentially the problem we're trying to solve is given a product, given features of a product, which is the text and the image, we want to find which branch within this taxonomy does that product belong to. Like that is essentially the problem, right? Now the taxonomy structure works great from a categorization perspective, but it makes our machine learning problem so much harder to define and train, right? Because normally when I say classification, most people assume a flat classification where you have n number of classes and I need to pick one. This is not that. This is I have different branches and I have to pick one branch that best describes that product. So before I jump into the model itself and the architecture and how we use today, couple of requirements that we had, right? Our vision in the end was to not just stick to product categories. We wanted to build all those other things, right? So shape, size, color, right? Like all of those other things, right? So we wanted to start building essentially a knowledge graph that we could then reuse for other tasks down the line, right? So we first of all started framing this as a multitask, multi-class problem. The idea is that we would have a central neural network graph with a lot of layers and nodes, and then a subset of each of those layers could be reused for different tasks by making the right connections between each of those layers, right? So what did that mean for us? Remember, I said the Google product taxonomy has different levels to it. In fact, it has 7 different levels. You could start at the very top, arts and entertainment, and then go all the way down to level 7, clarinet haircuts. So essentially, each level of that taxonomy is treated as a separate classification problem, right? So I basically say, hey, at level 1, what do you think the prediction is? Fine, great. Like then using that information, I come down to level 2, ask the next. So we have essentially these different tasks. We still train a single model, but the single model is now trying to do multiple tasks together. And each task is predicting one level of the taxonomy, right? And then obviously each task is a multi-class because you have multiple classes in each level, right? One key thing to remember here is not all levels are equal, right? Like every level has a different number of categories belonging to that level. For example, at the very beginning, there are a few nodes. Level 1 probably has 21 categories or something. By the time you get to level 3 or 4, you're now dealing with thousands of categories in that level, right? So not all levels are equal. If you remember our product detail page before, all of the data was unstructured, right? We had text and we had some images, right? We didn't want to reinvent the wheel, right? So there are a lot of pre-trained models already existing that we could kind of use to kickstart the learning process. So we said, hey, let's go and see if we can use some of these pre-trained models to help us do better. Specifically, we used multilingual BERT for text, and then we used MobileNet V2 for images, right? The choices of both of these models were essentially done after exhaustive testing. It essentially boils down to you use bigger models that will give you gains in performance, but it comes at the cost. There is a cost associated with it. And so we had to kind of find this balancing act between cost and performance, right? And so we ended up with these two, right? And then we had different consumers. Like I said, like there are so many different consumers, both internally and externally. And all of them had slightly different access patterns, right? Maybe somebody wants to access us in a database through batch prediction, right? Maybe someone wants to have real-time inference or streaming, right? And so then we realized the model has to be actually deployed in different flavors to accommodate all kinds of this. So we went with the subclass model architecture, and I'll dig deeper into what that means in a few minutes, right? But basically, you can either deploy the entire model as a standalone model, or you can chunk it up into pieces. And Jules actually touched upon this a little bit when he spoke about inference graphs a little earlier. You could essentially have this graph of models. What that enables us is to kind of then do things like caching of embeddings, for example, right? It actually gives you efficiency gains and boosts if you kind of split that out. And for different use cases, we've actually deployed the model slightly differently, right? So these were some of our decisions that we made initially, right? And then there's one last thing, and this is something that used to trip up all of us before, which is there were a lot of pre-processing that is specific to the model itself, right? And this things like, oh, how do I one-hot encode something? And I want to do that in real time. So we decided to go TensorFlow Transform to kind of help us do the stateful transformation. What that does is we use TensorFlow Transform during the training to kind of do all of the pre-processing. And then that pre-processing step is now essentially saved as a TensorFlow graph, which I can then use during inference time to do the exact same transformation, so that there is no difference in pre-processing between training and inference time. So having said all of that, now let's actually look at the model architecture. I've spoken quite a bit about all of the things we wanted to do. I'm not going to get too much into the specifics. Here's a very rough schematic of the model for the first 2 levels of tasks, right? Remember, there are 7 layers of tasks, one for each level of the taxonomy. So what we do initially is we take the raw text and we take the raw image and as separate inputs, pass them into their corresponding embedding layers. So BERT and image, MobileNet V2. We then pass the combination of these embeddings through a multi-layer perceptron to finally predict the first layer, right? Like the first level, right? So you'll pass the image, you'll pass the text, and then you kind of go, hey, I think this belongs to animals and pet supplies, right? You essentially get that score at level 1. We then take that output, combine it back with the original embedding. So we take the level 1 output, combine it back to the original embedding, and then pass that through a second multi-layer perceptron, right? And this second multi-layer perceptron, essentially it is focused on the second task, which is predicting the second level of the Google product taxonomy. And you do this over and over and over again until you hit level 7, right? So you predict level 1, take the predictions, or you try to predict level 1, take the output of that, concatenate it back with the original inputs, pass it through another set of layers, try to predict level 2, take the output of that, concatenate it back with the original, on and on and on, until you hit level 7, right? So while each, so what that essentially did is the parent node helps to predict the child node. And that makes sense, right? Because if I inherently told you, hey, something is, I think the first level of this is clothing, then the second level should have a higher likelihood of being a shirt or a pant versus a drill bit, right? So the parent prediction should affect the child prediction, right? And so that's why these connections made sense, right? The second thing, and we already spoke about this, right? Like there's 7 levels, 7 tasks, right? What we also then did is we have massive amounts of training data, right? We have massive amounts of data that we want to predict on as well. But in terms of just the sheer data we have to train on, it runs well into the hundreds of millions of products, tens and tens of millions, in fact, hundreds of millions of images, right? A lot of text. It can actually get very exhaustive. The training data set can get very, very big, right? So we had to do this in a distributed fashion, right? So we ended up using distributed TensorFlow with multiple GPUs, multiple machines. And this is where Ray Train came. Now, we did this over a year ago, and at that point, Ray 2.0 wasn't a thing. So this was all built on Ray 1.x. So Ray Train was what we ended up with that. At that time, we're using distributed TensorFlow. Right? And so we did that, and then we built so we use Shopify's ML platform. It says that it's built on Google Cloud Platform, but Google Cloud Platform is our infrastructure provider, right? Like that's who gives us our machines. There's Google Cloud Platform, there's Ray sitting on top of it, and then there's me, right? So I am essentially the user of our ML platform, which is called Merlin. There is a slide later where I'll talk to you about the architecture of how Merlin and Ray is being used. But essentially, our infrastructure layer is Google Cloud Platform with Ray sitting on top of it. And so you might be wondering, I said something like a minute ago where I said, well, if I predicted something as clothing and apparel at level 1, it should have a higher likelihood of being a shirt or a pant at level 2 and not a drill bit, right? Like you can very justifiably at this point ask me, but okay, it can never ever be a drill bit. It should always be either a shirt or a pant, right? And you're right. Like eventually when we expose this to our consumers, like if I predict clothing at level 1, I should never ever predict a drill bit at level 2. But during training, at least, the training is completely taxonomy unaware, as in we allow the model the flexibility to say, hey, if you think it's a drill bit at level 2 and if you're confident, you can do it. And there's actually a reason for this, because if you enforce the condition at the very beginning, then the model will never recover from a catastrophic failure, right? As in, if it gets the level 1 prediction wrong, it's never going to recover below. It'll always be wrong below, right? Whereas if you kind of during training, let it kind of say, give it the flexibility to deviate from the parent prediction a little bit, it allows the parent prediction to catch up due to the back propagation, right? So we did all of that for training, right? For inference, these were the requirements we had, right? I already mentioned we have multiple billions of products historically. We've connected tens of billions of images for these products. I'm not giving you the exact number because I can't talk about it, but we have a massive, large-scale data problem, right? And every time we train a new model, one of the requirements we had is we have to do a historical backfill of all products, right? So every product that any merchant has ever created at Shopify, I have to go back and basically predict on all of them, right? And then furthermore, we have tens of millions of products that are either being created or updated on a daily basis. All of this I'm basically telling you because dealing with this many images and products is non-trivial. Like it's extremely hard, in fact. Furthermore, like I said, we have many consumers who want to consume us from different access patterns. It's basically spans the whole range, right? We have consumers who are in batch, consumers in streaming, consumers in real time. We basically have to support all of those different use cases, right? So those were our scaling requirements. And so I remember I said, that's how we train the model. How we train the model is slightly different from how we actually use it for making prediction. So essentially, what we do is we chunk the model, right? We train this one big model and then we chunk it into smaller pieces, essentially almost like a Lego, right? So we want to make, like, we take this big model and chunk it into smaller Lego pieces. And then what the idea behind is each chunk can now be deployed as a standalone model, because then you can kind of go, hey, I've already seen this image before, so maybe I don't have to create a new image embedding for it. I can just reuse it from the image embedding cache, right? Or I've seen this text before, so let's not re-embed that text, right? So it gives us that kind of benefit. Or in the real-time case where you don't want to make these calls to go and fetch things from the cache and you want to do it right away, then you also have this big, the combined model that's the combination of all these chunks that can also be deployed as a standalone service, right? So we start off initially with the two embedding layers. Those are deployed separately as standalone models. Then we have what we essentially call the embedding to probability. This is the chunk of it, right? So this is going from, hey, you've given me the text embedding and the image embedding, and from these I'm going to essentially give you logit scores of all of the categories, right? And from there, remember I told you that the model is taxonomy unaware. We then impose business rules on top of it, right? We essentially say, hey, if you predict at level 1 clothing and accessories, you cannot predict level 2 as screwdriver, right? So that's where we kind of come back and we impose the taxonomy on it. And so we have all of these pieces, right? So the first two pieces are embedding models essentially. Second one is take the embeddings, make score predictions, and then the third one is take the scores, apply business logic on it to give the final refined prediction that we expose to our consumers, right? Now, each of this, you can basically take any combination of this and deploy it as and when we need. And we've actually deployed multiple combinations, permutations and combinations of this as and when needed for the use case. So I'm not going to stick, I'm not going to jump too much into this. We've already spoken about it. This is where we kind of come and say, during inference, we basically say, hey, give me the prediction at level 1 with the highest probability. Let's say that's clothing and accessories. Then I go back to level 2 and I say, out of all of those, I have scores for every node at level 2, but I basically then say, if I predicted clothing at level 1, give me only the scores of the children of clothing and then take the max of that, right? So that's how I impose the taxonomy during inference, and this is the slide that talked about that. I'm jumping a little bit here just to kind of get to the interesting Ray bit in a second, right? And then we also have some thresholding built into this, right? So because at the end of the day, it's a stochastic model, it can make mistakes. We want to kind of limit. We would rather not make a prediction than make a wrong prediction, especially in certain use cases. Like I don't want to wrongly predict something if I'm using it for taxation, right? So we do have some thresholding built in where we kind of go, okay, I'll go level 1, level 2, level 3, but at level 4, I'm not confident enough. And I'll kind of say, that's all I'm exposing. So in this example, you see that we're actually fairly confident about the first 3 levels. And then when we get to dog apparel, we're not confident. And we kind of go, I'm not exposing that to the consumer. So let's get to the interesting part, right? So what tools did we use? Ray is actually a very central component of what we did, because the ML platform for Shopify, which is called Merlin, is essentially built on top of Ray. And as a consumer, I interact with Merlin, right? But that also means I'm using Ray in the background, right? We use a few other tools as well. Spark was essentially the choice. Like Spark is the choice of tool for any kind of data wrangling at Shopify. So a lot of our pre-processing was done at feature engineering is done in Spark. We already spoke about TensorFlow and TensorFlow transforms and the TensorFlow extended ecosystem. Our infrastructure layer is Google Cloud. We also used a little bit of PubSub and Cloud Functions, essentially for us to make an image pipeline, right? So remember, this thing consumes images. So we needed an ability to kind of move images efficiently from our cloud storage location to something that's accessible by the model. So we built a custom image ingestion pipeline, right? So here's the interesting bit. So Isaac, who is from Shopify, has actually given a great talk in last year's Ray Summit about how we built the Merlin platform on top of Ray. And if you haven't already watched it, I hope there's a recording of it. You should. Right? This is a very high-level overview of what our data infrastructure looks like at Shopify. Right? So all of data, like I mentioned already, it's built on top of the Google Cloud Platform, right? And we've had for a few years now a mature data platform, which has been tried and tested for many, many years, right? And this has usually enabled our data scientists to consume a wide range of data sources, right? We've enabled our data scientists to process data using either Spark, SQL, or Flink based on specific needs of that team and that project, right? But over the last few years, we've realized that ML use cases have different needs that are in addition to what was already being provided by our existing data platform, right? And this is what led us to building our new ML platform, which is called Merlin, that's focused on solving these specific needs to complement the existing data platform. And so this is where Merlin comes in, right? Merlin's built, again, it's built on our GCP system. There is a Kubernetes, like we have a Kubernetes platform, and Ray sits on top of that, right? What Ray enables us to do is, as a data scientist, I basically go to our ML platform and I say, hey, I want to either prototype something or I either want to run something in production. And I essentially give a configuration file that says, hey, this many workers, this many GPUs, this much memory. Essentially, it's a config-driven system where I give a config file and say, these are the hardware requirements. Here is the code. Here are the software requirements. I essentially package all of that up in a repo, send it over to Merlin, and Merlin can then run that in the hardware, with the hardware and the software that I have specified, right? The concept of that is called a Merlin workspace or a Ray workspace for us, right? And the benefit of doing it this way is that whatever environment my thing is going to run in production is the exact same environment I'm going to develop or prototype any of this, right? So when I'm prototyping, I'm confident that the libraries and the hardware that it's running on is exactly the same thing as what I'm going to run in production, right? And so we have Ray, and then we have Ray workspaces, right? And Ray workspaces, on top of that sits our code, and our training and our prediction all sits there, right? Outside of the Ray workspaces, we also have complementary products within Merlin. So we have a modeled registry, which uses Comet. We have an online inference service. Today, the online inference service is bare bones and it's microservices architecture based. But for some of our more complex use cases, like product classification, we're currently investigating, we're actually prototyping to see if we can use Ray Serve to do things like inference graphs that Jules mentioned. And then we also have Pano, which is our feature store. This is built on top of Feast, right? So we have model registry, we have online inference service, we have Pano, but all of these revolve around the Merlin core system, which is built on Ray, and then we have the workspaces. So this is kind of the rough idea of how our data infrastructure looks like. Again, for more details, I am not a platform engineer or a data engineer. I am a consumer of this. For more details on this, I highly encourage you guys to look at the talk. We also have a blog post about it that Isaac gave in last year's Ray Summit. So we started, like I mentioned, we started working on this project over a year ago. And at that point, I do not believe that Ray 2.0 was released yet, right? We do have plans to kind of migrate over to Ray 2.0 at some point. But as of today, we use Ray Train for training, Ray Active Pools for batch inference. And then for online inference, we use our microservices-based architecture. So this is actually my favorite part of the presentation, right? Like typically at the end of a presentation about machine learning, people will kind of say, oh, I increased accuracy by this much, or my recall is so much, my precision so much, right? And we did all of that. Like, I'm not going to say we didn't. We did all of that. But to me, that's not actually the most important part of why you would want to do ML at this scale in Shopify, right? remember that admin page that we saw before, right? The one we saw earlier where we had all of that unstructured data. Let's go reacquaint ourselves, right? Like nothing has changed, right? It's the same image. There's a lot of unstructured data. At a high level, it looks the same, right? And then we made a change, right? The change you see here, it looks kind of the same. The one small difference is we've introduced this new field there called product category, right? And you'll see that it's actually blue. Whatever is filled there is in blue. What that means is actually, that's our prediction. That's the model actually predicting something, and it's put in front of the merchant, right? So as the merchant's typing, as you're creating something, let's say you type up and say dog bed, immediately there's a prediction there that says, we think it's this, right? And as the merchant gives us more and more information, in real time, we keep updating our prediction. Now the merchant has a choice, right? Like they can do one of three things. They can either accept what we're giving them, which is great. Like that's the best case thing. That's the best case scenario. They can, if they don't accept, they can come and edit what we've said, right? So if I've said dog bed here, they can come click on it and go through the taxonomy, and then they can correct me and say, no, I don't think it's a dog bed. I think it's a cat bed instead, which is also great because A, they've engaged with us and they've given us what the true category of it is, and we can use that for use cases down the line. B, it also gives us new training data, right? And so our model continuously now gets better as merchants interact with us, right? And finally, they can ignore us, right? We hope they don't do that, but there are certain use cases for which we cannot legally use the prediction, and we need the merchants either correcting us or accepting our prediction, right? But this actually happened, and so this immediately now, as of today, this gets used for search, it gets used for recommender systems, it gets used for automatic tax calculations, it gets used for channel syncs. There's a bunch of like automations and workflows that we immediately built on top of product classification that benefits our merchants right away, right? And there's also, remember, that feedback loop, and this is automatically getting better as merchants use it more and more, right? And all of this couldn't have happened without Merlin and Ray sitting underneath it, right? So again, this is honestly the least important slide for me, right? Which is how do you measure the ML metrics? We have the usual metrics that you would use for a classification problem. The only wrinkle in this is it's a hierarchical classification, right? So normally people talk precision recall. We talk hierarchical precision, hierarchical recall. We have coverage, lowest common ancestor. All of those are fairly self-explanatory. Again, more important product metrics, adoption and merchant acceptance, right? Like how many merchants actually use us and how is that then downstream being consumed, right? So what comes next? Well, we have to evolve and adapt the taxonomy. Like the taxonomy isn't like the Google product taxonomy was a great starting point for us, right? Like it starts off, but it was built by Google for Google, right? And we quickly realized our needs are a little bit more different than theirs, right? And so we've actually already moved away from the Google taxonomy. We've used them as a starting point and then kind of evolved from there, right? One of the other things is not all consumers are made the same, right? For example, taxation will say, okay, tell me exactly what this product is because I need to know, right? Whereas trust and safety will come and tell me, I don't really care about the difference between a shirt and a pant, but I really care if they're selling guns, right? Like they only care about certain specific categories. So different consumers have different use requirements. So we, instead of having this one model that fits everything, we could potentially have one core model and then multiple flavors of heads sitting on top of that to kind of service many of those consumers. And then, the last point we want to kind of, there is that tuning in the middle where we kind of say, remember where I said we do early stopping, that threshold tuning is currently manual. We want to kind of use merchant feedback to feed into it, right? And so these are things we want to do, right? So I did want to stop a little early to kind of give time for questions. So yeah, if you have questions, I would be more than willing to answer them today.
Well, thanks a lot, Kay, for this fascinating journey, how you actually sort of decouple, the data science group who are actually working on the actual building of the actually model and the infrastructure, which is completely abstracted away. So you as a data scientist, when you're actually building these particular models, do you actually do you write any Ray code like actors or anything, or is that completely abstracted away in the modeling workspace?
We do write some Ray code. Not that Ray's collect, because we still have to kind of, like I said, Ray train, right? So and actor pools, we still have to write that code to kind of we use some Ray core, so it isn't completely abstracted away. What is abstracted away is the ops part of it, right?
Okay.
So I don't have to I don't have to create a cluster, or I don't have to kind of like make sure that it auto scales. Like all of that is taken care of by the infra team and the platform team. My thing is, okay, I know I need to use Ray in a way that's minimally invasive to the rest of my code, right? So on this model predates us using Ray, right? Like it existed before we used Ray. And in fact, it was the first model that moved to Merlin when we used Ray. It was actually a piece of cake to move it to Ray, and which is great feedback that I can give for you, because the migration as a user for me to use Ray wasn't actually right. It was like a few lines of code that we changed, and boom, it works now in Ray, right? So yeah, like it's not that we don't use Ray; it's minimal.
But you did mention about how you're actually doing batch inference at scale. You're using Ray tasks to be able to do that, and then you're using Ray actor pools. And I think these are some of the things that we also have even not only in 2.0, but it also as part of the Ray Air. There are two ways to you can actually do inferencing. You can actually use batch inference at a massive scale using the Ray core APIs that you guys are using, right? You're using Ray tasks to do batch inference. You're using Ray pool actors to be able to do the batch inference. Or you can actually use the Ray data sets, and you can use the Ray Air predictor to do batch inference. Yeah. So there are sort of two ways to actually do that. And as you say, you guys predated Ray Air, so you didn't have the ability to take advantage of that. And I'm delighted to hear that you guys are thinking of migrating to what the Ray Air and 2.0.
Right, and exactly. And also remember, we are one level away from Ray, right? As in Merlin supports, like our platform has to support specific versions of Ray. So the day my platform team comes to me and says, hey, you have to move to Ray 2.0, that's when I'm going to have the discussion of migrating it over, because otherwise there is no product benefit to moving to Ray 2.0. Right? So as of today, it works with Ray 1.x. So I'm like, yeah, this works. Right? Having said that, for newer projects that we've tried, like we have moved on to Ray 2.0, right? 2.0. But again, this is the one of the pain points that I always complain about when there are breaking changes, like all of those changes between Ray 1.x to 2.x is kind of what happens to all of those things where we built it. Now that becomes a migration task over, which doesn't inherently have product value associated with it.
Right. And I think one of the things we are doing diligently is to make sure that we actually provide migration path. So the API is to a certain extent work backward compatible, but at some point, obviously they're going to be deprecated. But this is actually a good use case that you're actually telling us and sharing with us. There's a question from Swaroop who says, what would you say is the difference in velocity of model development time with or without Ray in your experience, since you're the consumer of that?
Yeah, I mean, I don't have a quantitative number, right?
Yeah.
But anecdotally, I can tell you, for me and my team, there is an increase. Like just that one point where that I mentioned, where hey, like at least the way Merlin is using Ray, where it kind of where I'm saying, hey, I have the exact same like the library, the software and the hardware equal like environment in production as I will have in prototyping. That is massive. Like I cannot understate how massive difference that is, right? Because typically dev and staging environments are less, like you probably see less of the data, it has less resources, and then you kind of have to move that over to production, and then there is some translation involved. But I have no such problems, right? Like in fact, we even have examples where we kind of go, hey, some data scientist trained something in some notebook ad hoc. Just know it'll work, right? We can in fact like even copy it over and say like use it through the registry in production, right? So the ability to kind of have the same environment is massive, and I think Ray enables a lot of that. And I also find myself using Ray quite a bit for things like monitoring. Like I use the dashboards. Like all of that is like a big win. Not to say it didn't exist before, but that one single place where it all exists is godsend, to be honest, right? And so, have I quantified it? No, but has it increased our velocity? 100%.
And just to add anecdotally what you said, and just to give my perspective on what Swaroop is asking, is that I think The goal and the mission of Ray is twofold. One is to make distributed computing programming a lot easier and very Pythonic, and anybody can actually do that. Distributed computing is not easy, right? In the old days, you actually had to write MPI code. You actually had to write very complicated code to actually understand. You had to worry about fault tolerance. You had to worry about memory management, as Clarence actually mentioned. All these are different aspects of it. Today with Ray, all the heartbeat is actually taken care of it. And so what we provide you is with these primitives that allows you to actually write distributed applications very easily with Ray task and Ray actors. So in that respect, the velocity is just astronomically faster compared to if actually we're doing writing distributed computing in the older way, because of the fact that we have extracted away with primitives that allow you to do that. And then we take, we do all the heartbeat about scheduling the task, about making sure there's a fault tolerance, about retrying, but giving you the ability to actually look into, as Clarence mentioned about. So yes, there is a huge improvement and velocity in terms of how fast you can actually write distributed applications using Ray. And it's very Pythonic. I think of it, Ray distributed computing is an extension of Python, really. You can actually kind of very easily if you come from that particular background.
So this is only half a joke. I actually joke to my platform team all the time that they're actually making it too easy, right? And I only say it's half a joke because if you're not very careful, it's very easy to write non-performant Python code and then Ray will distribute it across, and then you're just broadcasting your mistakes. So it's only half a joke, but you see what I mean, right?
Clarence, did you actually have any input on is there a difference in velocity between using Ray and not using Ray? I think you're muted. We can't hear you.
Yeah, I mean, definitely. I think like one of the big improvements, we've been making in the last, at least in the last quarter or more, is like around observability, and it has been one of the bigger pain points, at least like from what I'm learning from users around, like, because a lot of the development work, like part of it is writing code, but also a lot of it is around debugging. So we've actually made a lot of improvements in that area. I think that's how, like, especially like one of the critical features, for example, with Ray is like we have like distributed log like collection and filtering that it's not an easy thing to build. Like if I were to just build a framework that is not using Ray, it's quite a bit of effort to build. And so I think one of the nice things about Ray is that like these like observability things are coming for free. And for distributed application, if it's not for Ray, someone will have to re-engineer that.
Another question from Swaroop is that, have you explored using modem/Dask instead of PySpark?
Have I explored it? No. There's a reason for that, because Spark was just a natural choice because the rest of the Shopify data platform is built on Spark. We have an in-house tool that's an abstraction on Spark. So 99% of all of the data transformations in Shopify happen on that platform. And so Spark was just the natural choice for us because we had that tool. Having said that, I know there are other teams who are using, I think Dask on Ray is something that I know there are teams at Shopify using. Have I personally used it? No, but I know there is a use case for that.
Question from Alexandros Sharrington. Great talk. If you don't mind me asking you, how does the model work for different levels of taxonomy depth during training?
Yeah. So if I understand that question correctly, you're saying not every branch is equal, right? So for example, t-shirts is only level 3, but clarinet care accessories is level 7. How do I deal with it? Actually, it was very simple. We just introduced dummy variables. So if the label ends at level 3, then we introduce a dummy variable at level 4 through 7. So the model will always predict all 7 levels, except if it ends at level 3, it will then say everything. It will predict the dummy variable for every other level after that, right? This does introduce some imbalanced data set problems, right? We already have imbalanced data set problems. This amplifies it a little bit. but there are techniques to kind of overcome that, right? But essentially, the model will always predict 7 levels of prediction, but it will kind of say, hey, this is clothing, shirts, t-shirts, and then it'll say dummy, dummy, dummy after that. Yeah.
I think it's a multi-part question. I just ask you the first part. If you actually go to the Q&A question, you can actually see it. Where do you only consider the top layers that correspond to the level indicated by your labels? Example, fashion goes to dresses only use output. And if so, how does the fact that the different parts of the model are trained for a different number of iterations affect the overall performance? Yeah, if you actually want to get, are you on the Q&A? You can actually look at the panel. Just click on the Q&A panel.
Yeah, I see it. I see that.
Okay, you see it. All right. Yeah.
Yeah, I think it's like, I think fundamentally, like I said, because we introduced that dummy variable, it's the same number of steps and iterations for every product in the training and the prediction set, right? So the number of iterations is the same. We do feed in, right? So during training, we'll kind of feed the image to the first level, get whatever logit scores at level 1, feed that into level 2, level 3. We will continue to feed it into level 4, 5, and 6, right? Except the target variable is now a dummy variable that we've introduced, and it says, hey, this is almost, think about it as unknown class, right? So we've introduced this fake unknown class. And so the model will that's a legitimate prediction that the model can make, right? So it can say, hey, it's unknown class. It does end up going there.
The other thing that actually popped into my mind when you were talking about the merchant classification and you're getting daily images on, thousands and hundreds of images daily. So you actually, how often then do you actually retrain your model? Is it like on a nightly basis, or because when you actually have new images, they need to be classified and they have to go through the entire taxonomy hierarchical to be put in the classification. How do you account for the retraining of the model?
Yeah, so we don't retrain the model very often because what used to be a t-shirt before is probably still a t-shirt.
Yes.
So in terms of the learning capacity, like we probably retrain the model once every quarter. Like that's how, because it is an expensive model to train, right? Like
right.
For days, the whole thing trains for days. We have close to 500 million labeled data, right? Like products that are labeled. So it actually is very intense. Prediction, on the other hand, is different, right? Because every time the merchant updates the product, we might want to predict on it, right? So there are both real-time, like I said, real-time and streaming, real-time streaming and batch processes. So there are consumers where, as you're typing, like every time you move from one field to another, it actually makes a request to the model to say, hey, here's an image and here's the text, give me the prediction. There's also a thing where when you hit the save button, you've made all of your changes and you hit that save button, that goes into a streaming pipeline and it says, hey, the merchant's finished saving everything. Tell me what the final prediction is. And then we also have a batch process at the end of it because both real-time and streaming have failures. Like it's basically cleanup act at that end, right? So we missed this many thousand predictions yesterday and the batch process is going to clean it up, right? So we do all of that, right? But prediction happens almost instantaneously when the merchant makes the change. Training, on the other hand, we only retrain the model once every quarter or so.
So you don't worry about data shift. You're not worrying about any of the.
I mean, we monitor it. Monitor it, but it doesn't shift that much on a day-to-day basis. Right?
Well, we have 1 minute, and I don't see any last questions. Since I have the mic, I'm going to ask you a tongue-in-cheek question. Okay.
Sure.
I see those 2 guitars in the back. Did you buy them off Shopify? Or did you buy them at Amazon?
These actually predate my time at Shopify. In fact, some of my guitars I built myself. Right?
So, lovely. Well, that begs another question. Do you play the guitar, or are they just for display?
No, I do play the guitar.
Oh, lovely. Well, maybe next time we'll have 10 minutes extra so you can actually entertain us with your skill on guitar. Not only a data scientist who can write code in Python and Ray, but you can also play good music. That's a good combination. So thanks a lot on that note. We'll actually end that. I really appreciate you taking the time to share with you how you're actually using Ray at scale at Shopify and what are some of the challenges and problems. And we hope fully looking forward for you to making migration to Ray and 2.0. And I want to thank Clarence as well for giving us an insight and providing our lenses to figure out how to actually debug and detect our own monitor. For those of you, hope to see you again next month. Again, we have an all-exclusive European Ray Meetup. That's going to be early in the morning for those of you on this particular time zone. But I'm sure we'll have this cadence on a monthly basis. And if you have a story to tell us on Ray, make sure you actually submit your CFP. So see you next month. Have a good night. And thanks a lot for all of you.